Here's the scenario that breaks things if you get this wrong. You create an entity, ID 5, version 1. You destroy it. Some other system spawns a new entity, and it lands on the exact same slot, ID 5, but now version 2. Meanwhile, somewhere in your code, an old variable is still holding on to that first entity, ID 5, version 1, and it calls exists on it. If your engine can't tell those two apart, you just handed old code a live reference to the wrong entity's data. No crash, no warning, just silently wrong behavior. That's the bug this video is built around avoiding. Quick reminder of where we are. Video 1 was chunk storage. Components for a given archetype get packed together into a 16 kilobyte buffer called a chunk, with a header up front tracking entity count, offsets, and enable state. Video 2 was the entity itself. Just a U64, split by bit masking into an ID and a version. Today we answer the question that video left open. You're holding a raw integer. How do you turn that into an actual memory address? The answer is the world. Think of the world as an address book. The entity is the key. The world is what translates that key into a real position inside a chunk. Structurally, the world is a slot table for entities, plus a cluster of lookup tables for archetypes. The entity side is the heart of this video. There's a field, entities, a flat vec of EntitySpec, and the index into that vec is literally the ID half of the entity we split apart in video 2. Lookup is O of 1, just indexing, no hashing. Each entity spec holds exactly 5 things: arch ID, chunk IDX, IDX in chunk, version, has value. The first 3 are the full address, which archetype, which chunk within that archetype, which row within that chunk. Version gets checked against the entity's own version. Has value marks whether the slot is live or empty. And there's a free eaters queue, indexes that have been destroyed and are waiting to be reused. So the entities array doesn't grow forever as things spawn and despawn. The archetype side, briefly. Component types get assigned integer IDs the first time they're seen, so all future comparisons are on integers, not type IDs. A component set gets sorted and deduplicated before it's looked up, which is the detail that matters, because it means position velocity and velocity position resolve to the same archetype instead of 2 duplicate ones. There's a shortcut cache from a concrete type straight to its arch ID, a table mapping arch ID to the actual archetype and its chunk layout, a global version counter that bumps whenever a new archetype appears, so queries know their cache is stale, and a pool of reusable temp buffers to avoid allocating on every call. Spawning an entity has 2 branches. If free entity has something, pull that index, read its old version, increment it, and hand back an entity with the same ID but a new version. That increment is the entire reason version exists. If the queue is empty, the new index is just entities.len, and you push a fresh slot. Creating one goes in 4 steps. Get a new entity, find or build the archetype for that component type, insert the data into a chunk and get back a chunk yesh and IDX in chunk, and write that address into the entities slot. What the caller receives is still just one integer. The address stays inside the world. Checking whether an entity is still valid is 3 gates in sequence. Is the ID within bounds? Is has value set? Does the version match? That 3rd gate is the interesting one, and it's exactly the scenario from the opening. Entity A gets destroyed, Entity B reuses its slot with a bumped version, and old code calling exists on A gets false, cleanly, because 1 doesn't equal 2. No crash, no reading someone else's data. Destruction is where this pays off hardest. You read the address out of the slot and tell the archetype to remove that row. But chunk data has to stay contiguous, so removal is a swap remove. The last row in the chunk slides into the gap. That instantly creates a problem. Whatever entity used to own that last row now has stale data in its own slot. So the archetype hands back a swapped row, describing which entity moved and to where, and the world fixes that entity's slot to match. This is the whole point of having an indirection layer at all. The chunk is free to reshuffle its rows for the sake of contiguity, and the entity holding a plain integer never notices. If a caller held a raw pointer into the chunk instead, that would break the first time anything got deleted. Erasing the slot itself is simple. Push the index onto free ints, clear, has value. Leave version untouched until it gets reused. One more thing this file does that I'm not covering today. Changing an entity's components moves it to a different archetype entirely. That's its own topic. So to close the loop, the world is a flat slot table for entities plus a set of archetype lookup tables. The entity is the key. EntitySpec is the address. Version protects against dangling references. And that layer of indirection is what lets chunks freely rearrange their data without ever breaking a reference the user is holding.